Hi everyone, let's take a quick look at tonicity. Now, tonicity is the ability of a solution to influence the movement of water via the process of osmosis. And the way that this solution influences the movement of water is looking at concentration differences. So let's put that into some context. What we first need to draw up is a container. And we'll put a little bit of water in this container. And then we'll separate one side of the container from the other with a membrane. Now this membrane is a semi-permeable membrane, which means it lets certain things through but doesn't let other things through. And this membrane is basically a reflection of the phospholipid bilayer of our cells. Remember, the phospholipid bilayer is a double layer of phosphates and lipids. So you've got a phosphate head and a lipid tail, and you know that that's one layer, and then you've got the other layer which makes it a bilayer, and it goes all the way around, and that as well is a semi-permeable membrane. If we were to separate out one side of this container and call it side A from the other side, and we could call it side B, again it's a reflection of saying that we have side A, which may be the inside of the cell, and side B, the outside of the cell, and it's separated again by this semi-permeable membrane. Okay, so what's tonicity? Well, first thing is this. If we have a look at the concentration of some solutes, so solutes are just some sort of particles that are dissolved in some solvent or a solution. So let's just say side A, we have a fair few solutes dissolved in that solution. And then we compare it to side B, where there's not many solutes dissolved in that solution. Now, naturally, passively, without any energy, what will happen? Well, you should think, first of all, diffusion. And you should think, well, there's a concentration difference within this solution. There's a higher concentration on side A compared to side B. And if we look at that concentration, let's just make up a concentration. Let's say side A is 4 particles per litre compared to 2 particles per litre for side B. So you can see there's a higher concentration on side A compared to side B. Now, going back to diffusion. Diffusion is the random movement of particles or molecules from their area of high concentration to an area of low concentration. And these particles move at random, so they're bumping in all over the place. Now, if that semi-permeable membrane wasn't there, given sufficient time, the particles on side A would evenly distribute across the side B. But we know that there is a semi-permeable membrane in between, which means that those particles cannot evenly disperse across the side B. So diffusion is out of the picture at the moment. The next thing you need to think about is osmosis. Now, osmosis is the movement of water through a semi-permeable membrane from an area of high water concentration, which is this side, to an area of low water concentration, which is this side. And so what's going to happen is the water is going to move from side B across to side A. Now, your question may be, why does the water do this? And the answer is because it's this simple. When you have two solutions separated by a semi-permeable membrane that water can move through, all you need to do is look at them and go, which one has the higher concentration of stuff in it? Okay? And look at it and go, okay, side A has a higher concentration of stuff. What that means is this side has a higher osmotic concentration. Now, all that means is this. The more particles, the more likely they're going to pull water towards it. So think as though they're little men and they're trying to pull water towards it. So you've got a pulling force on side B, but there's not many men or women to pull towards them. And side A has a lot more people to pull towards them. So it's a competition. So water's getting pulled towards side B, but there's not that much pull compared to the pull coming from side A. So side A wins and it pulls more water towards it. Why? Because naturally things want to be balanced out. We want this concentration difference to be even. And if you think about it, how could we balance out these concentration differences? Well, diffusion, those particles could go across and it's even, but like we said, there's a semi-permeable membrane, so we can't. So what happens is the water from side B gets pulled towards the water, or those particles on side A, and then the water level on side A raises up compared to side B, and then what do you get? Well, we had 4 particles per litre on side A originally, and 2 particles per litre on side B originally, but now we've got more water on this side, which means we'll have 4 particles per 2 litre, which now is equivalent to 2 particles per litre. So now we've evened out the concentration. And that's osmosis, the movement of water. What's this got to do with tonicity? Well, let's relate this back to the cell. What if, for example, I were to, let's just say side A is outside the cell and side B is inside the cell, and we're separated by a semi-permeable membrane, and we've got a concentration of some stuff inside the cell and a concentration of stuff outside the cell. Now, did you know that if we were to calculate all the stuff that's dissolved in the cell and all the stuff that's dissolved outside the cell, that the concentration is going to be the same? It has the same osmotic concentration, which means outside side A, it's pulling water out towards it to the same degree that side B is pulling water into it. Okay, so it's balanced out. But we can change this, and as clinicians, you often do change this because you have blood vessels which are also in the extracellular fluid. Remember, you can separate out body fluids into intracellular fluids, all the fluid inside the cell, the extracellular fluid, all the fluid outside the cell, and that also includes your blood plasma. Which means whatever you put into your blood, basically it's going to be exchanged out into the extracellular fluid surrounding the cell. Okay? So if you were to introduce intravenously into a patient a high concentration of sodium chloride, so salt, well, what that means is all these particles that you're introducing of sodium chloride are going to leave the blood vessel and come out into this extracellular fluid surrounding the cell. Now, you know that this semi-permeable membrane will not allow things through that are too large or too charged. And sodium and chloride by themselves, sodium has a positive charge, chloride has a negative charge. They're not large at all because they're just charged atoms, but they do have a charge. So they want to diffuse into the cell to balance out the concentration, just like here, but they can't because they've got a membrane in between. So now what happens? Well, I told you all you need to do is look at the two sides and see which one has the higher concentration of stuff. And in this case, it's side A. Now what that means is the fluid or the water from inside the cell, side B, is going to be dragged out of the cell to try and dilute out this high concentration. Now what does that mean to the cell? It means that this cell will start to dehydrate and shrink. And this shrinking is called crenation. So, what do you think would happen if you were to inject into a patient a solution that was far less concentrated than the cell? So we just injected a solution that was far more concentrated than the cell. What happens if we inject a solution that's far less concentrated? Well, let's have a look. You've got a certain concentration of solutes inside of that cell, and you inject a couple outside the cell, so a solution that's less concentrated than inside the cell. Now what happens? Well, compare the two concentration differences. Inside the cell, B has a higher concentration than A, which means all these solutes will pull water towards it. That means that side B has a higher osmotic concentration and it's pulling the water towards it. What happens to the cell? It gets larger, starts to swell, and can sometimes burst. So that's the basic premise of tonicity, but let me give you some specific examples. Some examples you might find in your exam. So, there are some terms you need to be aware of for tonicity. One term is called hypertonic. What does hypertonic mean? Hyper means more than, and tonic is referring to concentration differences. So a hypotonic solution is a solution that's more concentrated than inside the cell. Hypotonic solution has a greater concentration than inside the cell. What about a hypotonic solution? A hypotonic solution is less concentrated than inside the cell. And what about a solution that's called an isotonic solution? Iso means same, and tonic is concentration, so it's the same concentration as inside the cell. So if I were to give you a question in an exam which asks, okay, you were to introduce to your patient intravenously, or you were to place a cell into a hypertonic solution, what would happen to the cell? Well, what you would do is you go, okay, I've got my cell, I've placed it into a hypertonic solution. That means the solution is more concentrated than the cell. You can draw it out like this and go, okay, the solution that's surrounding the cell is more concentrated. That means it has a higher osmotic concentration. It will pull water out towards it to try and balance it out. And then what happens is that in a hypotonic solution, the cell will shrink or crenate because it begins to lose water. Okay, what happens in a solution that's hypotonic? Well, that means you've now placed the cell into a solution that is less concentrated than that of the cell. You look at the concentration differences, and the water will be dragged into the cell because the cell has a higher osmotic concentration. The cell starts to swell and can burst. An easy way to remember this is hypo, nice and round. The cell becomes nice and round. Or hippo, big, fat and round. That's what happens to the cell. What if a cell is placed in an isotonic solution? Well, iso means same, which means if you were to calculate the concentration of particles inside the cell compared to the concentration of particles outside the cell, they would be exactly the same. What that means is the net flow of water outside the cell is balanced out by the net flow of water into the cell, and there's no cell size changes. This is tonicity. And this is important clinically because there are some solutions that you may have to deliver to a patient that are hypertonic, hypotonic, and many that are isotonic. And now you know what will happen to the cell and some cellular changes.